Welcome to this lesson on viscosity. Viscosity is a fundamental property of fluids that explains how they behave when they flow. Understanding viscosity helps us make sense of why some fluids like water pour quickly, while others like honey move very slowly. This concept is crucial in fluid mechanics and has numerous applications in our daily lives and in various industries. Viscosity is a measure of a fluid's resistance to flow and internal friction between its layers. When a fluid flows, its different layers slide past one another. The friction between these layers creates resistance, and this resistance is what we call viscosity. Think of it as the fluid's thickness or stickiness. Fluids with high viscosity have strong intermolecular forces that create a lot of internal friction, making them resist motion. On the other hand, fluids with low viscosity flow easily because their molecular structure results in very little friction. Let's look at two common examples that perfectly illustrate viscosity. Water has low viscosity, which means it flows easily with minimal resistance. You can pour water quickly and it spreads rapidly. In contrast, honey has high viscosity, flowing very slowly with high resistance. When you pour honey, it moves in a thick, slow stream. This difference is due to the molecular structure and the strength of intermolecular forces in these fluids. Honey molecules have stronger attractions between them, creating more internal friction. To understand viscosity better, we need to explore what happens at the molecular level. When fluid layers slide past each other, molecular forces between neighboring molecules create friction that resists this motion. These intermolecular attractions act like tiny forces holding molecules together. The stronger these forces, the greater the internal friction, and consequently, the higher the viscosity. This internal friction is the fundamental reason why different fluids flow at different rates. There are two main types of viscosity: dynamic viscosity and kinematic viscosity. Dynamic viscosity, represented by the Greek letter eta, measures the internal resistance to flow. It tells us about the force needed to make a fluid flow at a certain rate. Kinematic viscosity, represented by the Greek letter nu, is the ratio of dynamic viscosity to the fluid's density. It tells us how fast a fluid moves when a certain force is applied. Both types are important in different applications, and understanding the distinction helps in selecting the right fluids for specific purposes. The dynamic viscosity can be described using Newton's law of viscosity. The formula states that eta equals tau divided by the velocity gradient dv by dy here. Tau represents the shear stress applied to the fluid, and dv by dy represents the rate of change of velocity with respect to distance. The SI unit of dynamic viscosity is Pascal second, abbreviated as Pa times S. This formula helps us quantify exactly how much a fluid resists flow under applied stress. Several factors influence the viscosity of a fluid. Temperature is the most important factor. For liquids, higher temperature leads to lower viscosity because increased thermal energy allows molecules to overcome their attractive forces more easily. Molecular structure and intermolecular forces also play a critical role. Fluids with larger, more complex molecules or stronger intermolecular attractions tend to have higher viscosity. Pressure affects viscosity too, particularly in gases more than in liquids. In gases, increased pressure can increase viscosity, while in most liquids, the effect of pressure is minimal. Viscosity has countless practical applications in the real world. In automotive engineering, engine oils and lubricants are selected based on their viscosity to ensure proper lubrication and reduce friction between moving parts. In food processing, viscosity is crucial for controlling texture and consistency of products. The pharmaceutical industry relies on viscosity for formulating medications and ensuring proper drug delivery. In medical diagnostics, blood flow analysis depends on understanding the viscosity of blood, which can indicate various health conditions. These examples show how viscosity is essential in engineering, manufacturing, food science, and healthcare.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.